So what I want to do today is look at organic chemistry, and there's just a few things I want to revise quickly. The first thing I want to revise is, can you remember the difference between an ionic and a covalent bond? Do you remember? And then under covalent we had polar and nonpolar. Do you remember the difference?
Yes.
What is it?
Okay, covalent is when they share
Share what?
electrons.
Great. Ionic?
Ionic is when the other one takes from.
Good. So you give an electron away,
Yes.
and covalent is where they share it. Okay. Polar and nonpolar.
Thank you. Polar is when they have charged poles.
Charged poles. Well
And
done.
then non-polar is when they don't.
When they don't. Great. So there's kind of this little scale, okay, where if we look at the difference in electronegativity, morning Makani. If we look at the difference between the electronegativity, if the difference is 4 or close to 4, that's the strongest ionic bond you can get, and that would be something like, that's too strong, you don't really get anything that's that strong, but that's difference in electronegativity. Electronegativity is then that measure that tells us how much does a substance desire to get electrons. Okay, covalent bonds was when the difference of electronegativity was less than 1.7. Okay, then it was covalent. Was that true? Yeah. And if it was less than 0.4, then it was nonpolar. So in other words, in a covalent bond can still have poles, and then the ionic bonds always have poles. One is positive and one is negative, because one took an electron, so he's got extra. The other one gave electrons, so he's got less. Okay. So also, obviously, the more electrons I took, the more polar I'm going to be. Like if I took 2 electrons and you gave me 2 electrons, then I have much more electrons. And so, for example, sodium chloride, and what can we use? Oxygen, magnesium oxide. Okay, oxygen gave 2 electrons. Oxygen took 2 electrons, magnesium gave 2 electrons. So obviously this one's charge is much higher in the positive side, and that one's charge on the negative side is higher. So this molecule, this one gave 1 and that one got 1. Okay, so the charge on these two molecules, on this molecule, or this yes, I suppose the charge that exists on this molecule, if I have my magnesium and my oxygen bonded together, one side will be positive, one side will be negative, and for the magnesium oxide molecule, that charge will be bigger than for the sodium chloride. Does that make sense?
Yes.
As well? Okay, but now as we go, this one definitely has 2 extra electrons. This one has, so he's electron rich, that one is electron poor. So as we go on, further down this bonding that we get, it's more like the electrons gets drawn towards the middle. So perfectly covalent bond, something like hydrogen and hydrogen together, okay, the electrons they share is straight in the middle. Does that make sense?
Yes.
Okay, so that there's no positive or negative side for any one of them. Okay, the electrons are evenly distributed. That would make perfectly covalent. Now this is important because I'm primarily going to focus on the properties today, and how you can understand what forces are at work, as well as what effect does the forces have on the properties. Properties like the state, whether it's in a gas, liquid, or solid phase at room temperature, what properties how does it affect the boiling point, things like that. Okay, so that's why this is important, because if I have a polar molecule, so this is nonpolar when I don't have poles, and polar if I do have poles. distinct positives and negative signs. When I do have poles, two molecules that have poles, let's draw a molecule that have a pole. Here's one molecule. It has poles. The one side is positive, the other one is negative. So we have a positive and a negative pole, and then what happens, it will attract another polar molecule that is on the one side negative. The negative will be drawn to the positive, and the positive will be drawn to the negative. Okay, what did we call the forces when I give away an electron and you took my electron? We became cation and anion, isn't it? When I gave away, I became a cation. What did we call the forces that exist between the two atoms?
Intermolecular forces? Interatomic.
Interatomic, because I'm attracting two atoms. But now, because there's two molecules attracting each other, because now the molecule is polar and it's attracting other molecules because other molecules are polar as well, what do we call those forces? Okay, so when two molecules attract each other, that's called intermolecular forces. Okay, and it's these intermolecular forces that determine the properties of a compound. Okay, so the bigger the charges are here, the stronger that force is going to be. Okay, now what happens as we get towards the covalent direction, in other words, as the difference in electronegativity becomes smaller, the charges between them also become smaller. Does that make sense? Because now the electrons aren't at extreme ends, they're more towards the center. As we, instead of taking it and taking it, we're now rather sharing it. But again, when I get to polar covalent bonds, yes, I'm sharing it, but the one is pulling harder on the electrons than the other one. Okay, and a great example is when we have, for example, hydrogen bonded to a high electron negative element. So here's hydrogen. It's bonded to a high electron negative element. Now, which elements on the periodic table have high electronegativity?
Chlorine, maybe?
Chlorine, then oxygen, then chlorine, then bromine, then iodine, then sulfur. So notice these ones here. So they are all high electronegative, which means, and so high in the sense of, okay, iodine not that high, okay, not really that, and nitrogen is also high, okay, primarily oxygen, fluoride and chlorine, they're the highest ones, maybe bromine as well. Okay, so let's focus on those three. Hydrogen is only 2.1. He's pulling, that's his ability to attract electrons. This one, fluorine, is 4, oxygen 3.5, chlorine 3, bromine 2.8. You see 2.5 is getting little now. Nitrogen still 3. So when hydrogen is in a tug of war for electrons with other of those elements, they will win the tug of war. So they would get more of the electron, or the electrons in that tug of war, instead of being somewhere here in the middle, they will be more congregated towards the hydrogen. Towards the either oxygen, fluorine, chlorine, bromine, maybe even nitrogen. And what happens now, the problem with nitrogen is he wants too many. Okay, so he wants 3. So it's very unlikely that he can get 3 from one hydrogen. No, he can't. Okay, so it's mainly oxygen. Oxygen even needs 2. But still, whenever hydrogen is connected to an electron negative element, this is called a hydrogen bond. hydrogen bond, and then the forces that exist between other particles, because now what will happen is this will definitely be a polar molecule, and a very polar molecule. So this will be called hydrogen bond forces. Okay, in other words, between two molecules of hydrogen bonded to an electronegative element, high electronegative element, there will exist a force called hydrogen bond forces. One example of hydrogen bond forces exists in water. Okay, so when something is ionic, it is very likely to be a solid, because the forces that exist between the particles is very strong, because one is positive, the other one is negative, so they really attract the forces very, very strongly. As we come to covalent, perfectly covalent bonds, there's no force that exists except normal gravitational force that exists between particles. All bodies have a gravitational force existing between them. Okay, so there's only that, but it's so small that it's almost negligible. So what happens now is all particles contain energy because of their motion. They're moving. Now, if your kinetic energy is smaller than, or let's say much smaller than the intermolecular forces, you'll be a solid, because your motion isn't strong enough to get away from the attractive forces of the other molecules. So you're stuck together like this. Okay, like I showed you now. You're stuck together like that. Okay, and on a small scale, if we stuck together, on a large scale we form a solid. Does that make sense? Now, if my kinetic energy is still smaller than my intermolecular force, but the difference is not so big. Sorry, yeah, I tried drawing the kinetic energy smaller than the intermolecular force. Do you see that? So here it's still smaller, but they're comparable, which means like the thing is trying to move, the forces is keeping it from not moving too far. Do you understand it? So it's not, the kinetic energy is not big enough to escape the attraction. Does that make sense? And then we will have a liquid. Does that make sense? So it's not able, so for example, if I put a drop of water here, it wouldn't escape into the air. Well, all of it wouldn't. Only the surface, only the molecules at the surface will start escaping to the air. That is called vapor. Okay? And as the surface is escaping slowly, new molecules are coming to the surface, they have enough kinetic energy to escape. Why do they have enough energy to escape? Because they're at the surface. Their kinetic energy is only affected by the molecules below them. Does that make sense? Yes. While if you're underneath, your kinetic energy is affected by molecules all around you. Does that make sense? Yes. Okay. So liquids also start having vapor. Okay. Now, the weaker the intermolecular force, the more vapor will be released. In other words, vapor is that molecules on the surface that can escape. So if the stronger the forces are, intermolecular forces, the more the molecules can hang on to their friends on the surface. Does that make sense? Okay? Now, as soon as the kinetic energy is larger than the intermolecular force. Now, I'm comparing forces with energy. That's not the same thing. It is comparable, not directly. Energy is force times distance. I'm just showing it, I'm just trying to make a relationship for you between the forces that exist and energy. So they're not comparable in the sense that numbers are comparable. So I can't say molecular force is 2, kinetic energy is 1, and so the one is bigger than the other one. I'm just saying that as the forces increase, the kinetic energy's ability to escape decreases. Does that make sense? Okay. So if the kinetic energy is sufficient to escape the intermolecular forces, I will have gas. Okay, I won't have gas, but the substance will be in a gaseous form. Okay, so what that means, remember what is a gas? A gas is something that cannot be contained unless I put it in a container. While liquid, I don't have to put on the lid to keep the liquid. The solid, I don't have to do anything. The forces that exist between the particles are strong enough that they will keep themselves. In a liquid, I at least need to just put it in a container and it will take the shape of the container, but I don't have to close the lid, it won't escape. Gravity will hold it all together. Okay? But a gas, there's no forces between the particles, well, hardly any. Okay? There can be some, but hardly any. It's not enough, and so the particles have enough energy to escape. Make sense? Okay, and now you can see it all comes back to the electronegativity of the elements, because the difference of electronegativity. Because the larger the difference is, the more polar they will be. The more polar they are, the stronger are the intermolecular forces. The stronger the intermolecular forces, the more likely they are to be a solid. Make sense?
Yes.
Makes sense. So let's go to organic chemistry and try and understand all of that. So I'll get back to this in just a minute. First of all, you need to know that organic chemistry always contain a carbon atom. At least one carbon atom. So if something contains a carbon atom, it forms part of organic chemistry. Now, why is carbon so special? If you go and look at carbon, in here you'll see carbon has how many valence electrons? How do we find the valence electrons on the table? It's 4. We look at the group. So he has 4. How many does he want? No. Okay. Oh yes, extra. How many valence electrons do everyone want? 8. So how many does he need? So how many does he want? He wants 8. How many does he have? He has 4. How many does he need? Needs 4. So he has the same number to give away than to get. So he's very likely rather to share. You understand? So he has 4 valence electrons to share. So usually we will write him like this. Here's carbon. He's got more than, he's got 6 electrons. And there's the 4. Now his electronegativity isn't high, but it's also not low. Okay? So if you look at it, he's got a 2.5. So it's higher than hydrogen. Okay? So in a tug of war with hydrogen, they're slightly towards him, but not much. Okay, 0.4 is just on the verge. 2.5 minus, remember he was 2.5, hydrogen is 2.1. So the difference is on the verge of being non-polar and polar, do you understand? So I mean, he's the lowest polar molecule that you can get if he shares with hydrogen. Okay, so he's got 4 valence electrons. The simplest carbon atom is then when we take simply hydrogen giving or sharing his 1 valence electron, and they share it like that. Okay, but now he's got 3 left, so he's going to share with 3 others like this, in this sense. And then we come to a special naming method called IUPAC naming method. And in IUPAC we count the number of carbons. 1 is meth, 2 is F, 3 is prop, 4 is bute, 5 is pent, 6 hex, 7 hept, and you won't get more than 8, which is oct. Okay, so these are important. And now the moment I have a carbon, it is called an alkane. And this specific carbon is called a hydrocarbon because it is hydrogens and carbons. Okay, now if I were to have another carbon, This one, since we have one, I know you guys know this, I'm going to go through this very quickly. This one is called meth, because there's one carbon, methane, because it's an alkane. So if we have two carbons, it means I've got those 4 valence electrons, but one of the valence electrons is shared with a carbon. And so this carbon has 3 left, that one has 3 left, so all the rest gets filled up with hydrogens. I'm not going to draw all the hydrogens, you have to. Okay? And this one, since it has 2 carbons, it's called ethane. And so we go down until we have a whole string. So octane would be 8 carbons. I'm not going to draw them all. 8 carbons connected with single bonds. In other words, each carbon just shares 1 electron with another carbon. 6 carbons like that, 8 carbons like that would then be called octane. Okay, you guys know all this thing? Are you comfortable with all that? Okay, so what could happen now is that I could have that one carbon decides to share 2 of his valence electrons with another carbon, but because he's sharing 2, this one must also bring his to the party, so he also shares 2. And now this is still a hydrocarbon because it's still just hydrogens and carbons, but this is called an alkene. And so the only thing that changes, instead of ending on an ane, it ends on an ene. So this is ethene. And even if there was just one double bond in there, we would have called this octene. Okay, but there might be 2 double bonds in there, and then it would be called octdiene. So the diene would tell me there's more than one. Triene, there would be how many?
3.
There would be 3. But now I just need to say, where are those double bonds? So I'll need to number my carbon chain so that I can say where the double bonds are. So I'll start with the side where I'll start on the side numbering so that if I number from that side, my first one will have the lowest number. Okay, so for example, if it's like this, carbon, like that, you'll see I won't start numbering on this side, 1, 2, because my first diene, my first alkene, my double bond, is now on the second carbon. While if I start numbering from this side, my first double bond is on the first carbon. So I'll number so that the numbers I write here, I'm going to write my numbers I'll show you, 1, 2, 3. So there's a double bond on 1 and on 3. So I'll write it 1 and 3. If I numbered from this side, it would be 1, 2, 3, 4. It would have been 2 and 4. Okay, so I'll number so that these are the lowest possible numbers. Make sense? Okay. So that's the alkenes. The third thing that might happen is I might have that one carbon decides to share 3 electrons with another carbon that must also share 3, so we get a triple bond. Now it only has 1 left to get a hydrogen. This one has 1 left. You can either get a hydrogen or you can connect to another carbon. So the moment I have 3 bonds, it's called an alkyne. And the name now just changes. This first one could have been, sorry, that should have been ethene, could be ethyne. Ethyne would be a carbon double bond, triple bonded to another carbon. No matter how many other carbons there are, if there's one triene or one triple bond, it will be an alkyne. Okay, so again, same thing applies. There can be more than one, then it would be a diene or a triene, and then I'll just need to number to show where it is. Even if there is only one, I still need to number unless it is on the first carbon. Then I don't have to number. So if I had a triple bond, for example, here, the rest is all single bonds, then I'll number from the side. So here's my triple bond. I'll start 1, 2, 3, 4, 5. While if I start on this side, it would have been 1, 2, 3. So it will either be 2 or it will be 3 if I number from this side. 1, 2, 3. I'm going to choose the numbering that makes it the smallest. So this one would have been 1, 2, 3, 4, 5. Sorry, I messed up here. This wasn't octene, that was pentene. Okay, so this is 1, 2, 3, 4, 5. 5. Sorry, not 5. Pent. 2. Ion. Okay. Now, not unless this is a 1, I will have to number. If it was pent 1 ion, I could have left the 1 out. Okay. If there's nothing, it means it's on the first carbon. Makes sense, huh? Okay. Now, carbon, in these ones, we've always looked at carbon bonded either to a hydrogen or to a carbon. And whatever bonds he had left, that was bonded to hydrogens. Okay. Now, there's another one called let's quickly just look at here the forces. What type of forces exist in hydrocarbons? Okay. In a hydrocarbon, we now only have carbons bonded to carbons. What type of bond is a carbon to a carbon? Yeah. What type? Covalent or ionic? Covalent, because they are literally sharing it perfectly in the center. Will it be polar or non-polar? Non-polar, because they're pulling with exactly the same amount of force on those electrons. Okay, so the carbons will be non-polar. How about with hydrogen? So on the other side, on one side he's going to have 3 hydrogens. Okay, or at least more hydrogens than in the middle. Okay, what will happen at that point? Hydrogen, let's go to the table. Who's pulling the hardest between carbon and hydrogen? Carbon. Now again, we see carbon is 2.5, hydrogen is 2.1. So carbon is pulling harder, but if we go to our table, is that polar or non-polar? It is on the verge. It's basically non-polar, really. Okay, because it's only really polar once it gets there. Understand? The closer I get here, the more I'm polar. The closer I get there, I'm more non-polar. Okay, the difference is so slight that it can hardly be noticed. So what happens in these molecules? If I had my carbon, there's my carbon. And let's look at methane, for example, with my hydrogen, 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 hydrogen. Okay? All of the electrons that are being pulled by carbon is pulled slightly towards the center. Just slightly. Okay? Not enough to change the charge on hydrogen. If it does, it's so slight. So small. So there's hardly a positive charge on the other end. Hardly. Okay. So methane by itself hardly has no charge. It's non-polar, it's slightly, so there's a slight attraction between methane molecules and other methane molecules. So what do you guys think? At room temperature, methane would be in what form? What would it be? A solid, a liquid, or a gas?
It's a liquid.
Saying it's a liquid.
Yeah.
Justify that answer.
Methane isn't it?
Under standard conditions as well. So methane, under standard conditions means a pressure of 1 atmospheric pressure, temperature of 25 degrees Celsius, and concentration of 1 molar.
So methane is a gas.
Methane is a gas.
Yeah.
Why?
I was from life science and
Since it's yeah, I also know that.
The question is why?
Exactly, decomposition.
not strong forces maybe.
Yeah, is that what you're saying? You will speak up, please. Yeah?
Exactly, it acts as a gas released on the composed component.
Yeah, but that's not why it's a gas. It's not gas because it's released as a gas. It's a gas because of the forces that exist between them. So if they ask you why is something a gas, it can only be one reason. Because the kinetic energy is sufficient to escape the intermolecular forces. Now at room temperature, kinetic energy is not much, which means the forces must be very little. But
So
we know
have
that
to explain it according to chemistry. You don't have to interpret.
I don't know how you have to explain it in life sciences, but if they ask you in life science anything about methane, obviously you don't need to use chemistry to explain it. But do you guys understand why is methane a gas? Because the particle is nonpolar. There is no attractive forces between one methane and another methane. So they just go, yeah. There we go. You understand? Okay. Now what happens is we have another molecule. So we're growing him a little bit bigger. Okay, try it again. So here's my one methane. And now I am adding another molecule, not another molecule, another carbon. So now I have ethane. Okay. Now what happens is all of a sudden that molecule is slightly bigger. Actually double the size, almost. Not exactly, but almost. Problem, and what now happens is because electrons are freely roaming about, when I had one molecule like this, not one molecule, one carbon, I had a very small molecule. So when electrons were traveling around, they didn't have a lot of space to move, okay? But now in my bigger molecule, there's more space to move. So the chances that as they're moving around, that they congregate. In other words, like all of a sudden there's just a few electrons here, hey guys, then they're gone again, okay? But the chances that, because there's more electrons, the chances that they congregate is higher. Does that make sense? There's a bigger chance that for some reason, doesn't matter why, but for some reason there's all of a sudden a grouping of electrons right there. And when that happens, there's a negative charge. Now, if there's a grouping on one side, it means if one side is electron rich, the other side is electron poor. So then all of a sudden there's a positive charge there. Now, what this means is that we created a dipole, or a dipole was created. Dipole means two poles, okay? But this dipole doesn't exist permanently. It's not a permanent dipole, not like it's the whole time negative there and positive there, okay? It's called an induced dipole. Induced. It's induced because induced, for example, you get induced labor. Induced labor is when a woman is pregnant, she needs to deliver the baby, but something is going wrong and she's not going into labor, so the baby is not coming, but he must. She's in danger. The baby's, my wife, for example, Noah, was born through induced labor because he wasn't getting nourishment from the womb. So they had to get him out as soon as possible, otherwise he would have starved. So they had to induce her to go into labor. So in other words, it is something that doesn't come past normally, come to pass normally. It is caused by other effects. You understand? So this dipole means I've got two poles, a positive and a negative, but it's induced because it's not a permanent, it's not normal circumstances, it is caused by another effect. And this is caused by the effect of electrons congregating, just for some other reason, briefly, and then it's gone again. So, the forces that exist between two ethane particles is still very small, because the chances of this happening is small, but it's higher than the chances of that happening, of induced dipole forces happening here. Okay, because the molecule is bigger, which means there's more space for them to move, which means if there's more space for them to move, it's more likely that two people, so for example, if we just travel in this space, okay, or we even make this space smaller, then the distance between us isn't that large. So if we congregate like we are now, we're congregated, so that side would have been positive, this side is negative, assuming we're electrons. But now imagine we're moving around. Do you understand? Now the chances that we're this many on this side is quite low, because there's little space to travel. We might be here for just a moment and then someone goes there again. Does that make sense? But if we make it the place bigger, now there's a lot of space to travel. Now, while two of you are there, two might be in the middle, so there's electron poor on this side. You understand? So as the molecule gets bigger, and not just that, but there's many, and when the molecule is bigger, there's more protons. If there's more protons, there's more electrons. If there's more electrons, it means the chances of there being extra electrons on one side is bigger. Make sense? Okay, so that's what it comes down to. So what happens now is as this chain of electrons gets larger and larger and larger, the chances or the induced dipoles gets more permanent in a sense, because the whole time somewhere there's a congregation of electrons. Does that make sense? While here it might happen, but just for a brief moment, then there's nothing in for another brief moment. So as we look at, and I can maybe look at that. Okay, so look at this. Here's for example a diagram where they've looked at the number of carbons versus the temperature at which that thing will boil. Now, what is boiling point? If you just go back there, let me explain that. Okay. In order to increase something's kinetic energy, I need to give it energy. If I wanted to take these molecules, I wanted to give it energy, I need to heat it up. When I heat it up, it will start, what heat actually just is the motion of electrons. Okay, that's why metallic bonds are good conductors of electrons, because they are moving electrons. So if I heat this up, I will give it more energy. If it has enough energy, it can escape the bonds because it's trying to move, but it's stuck to the others. But if I can move it enough, it will start escaping. You understand? So all I need to do is add heat. Now, if it's a solid, it's still stuck to the other ones. So if I increase the energy, so in increasing kinetic energy, it means I'm increasing temperature. Okay? At some point, it is like it's stuck. At some point, it becomes fluid. Okay? Because I'm giving it enough kinetic energy so it becomes, but still a little bit stuck to these ones. Okay? Now, this would be called the melting point. Melting point is that temperature at which the particles have enough energy to start becoming fluid. Okay, still stuck to one another, but they can now move around because they've got enough energy. But you can see as I'm moving this one around, it's still not pulling away. If I continue to increase the energy, at some point, I'm going to increase it so much that the particles start escaping. Okay, so moving it so much, and now, oh, there it goes. Okay, now that point, the temperature at that point is called the boiling point. Okay, so boiling point is the temperature at which particles start escaping from the surface rapidly into space. Make sense? Melting point, or other way around. The boiling point can also be the temperature if I'm going down. It is the temperature at which, as I'm going down, at this temperature, it starts condensating. Okay, in other words, starts becoming liquid. So going from liquid to gas, boiling, going from gas to liquid, condensation. Then going from, I can't remember what you call, I can't remember what you call it when you go from a liquid to a solid, but the same with the, sorry?
Freezing.
I suppose you could say freezing. Makes sense.
Yeah. I think that's how we call it.
Is it? Freezing. Okay, so going from a liquid to a solid is the same melting point, is also the freezing point. Does that make sense? We're just going in the opposite direction. I'm going now from higher temperature to lower temperature. So if I look at room temperature, here's my melting point will always be less than my boiling point. Does that make sense?
Yes.
Because I'll melt first before I can evaporate. Make sense? Now I must see where is room temperature in order to know what state it will be in a cup. If room temperature is less than the melting point, will it be a solid, a liquid, or a gas?
If room temperature is?
So room temperature is less than the melting point.
It's not solid.
Well done, because it's room temperature, not melted. Make sense? If room temperature, now remember, room temperature is fixed. You can't change room temperature. It's 25 degrees Celsius. Well, 25 degrees Celsius. Okay, so room temperature is a fixed value. Boiling point and melting point varies per substance. So methane has a fixed boiling point, but ethane has also a fixed one, but different from methane. Does that make sense? Okay. So the room temperature. Why am I saying room? P. Room temperature. If room temperature is between melting point and boiling point, it will be liquid. And if room temperature is more than the boiling point, it will be gas, because at boiling point it turned gas. So if I have it at room temperature, I've passed its boiling point. Does that make sense? Hey, Bonnie!
Yeah.
Okay, so with that in mind, let's quickly look at each of these substances. Okay, here you can see that this is now with one carbon. That would be about one carbon. I'll try zooming in a bit. With one carbon, these are all boiling points. One carbon, my boiling point is at where? Roughly negative 100 and something. Okay, 100 and maybe 70, somewhere there. You see that? So at room temperature, methane is?
Solid.
It boils at negative 190 degrees. In other words, can you imagine how cold negative 190 degrees is? You're dead. When you enter that environment, you're just dead. You're just frozen solid immediately. Everything about you is frozen, and yet methane is boiling.
Boiling, like boiling.
It's boiling like water would be boiling. Methane is boiling when almost everything else is frozen, absolutely solid. Why? Because there's no forces keeping it together. Do you understand? Make sense? So, at room temperature, methane would be gas. Okay? Ethane. Now notice, all of a sudden, the boiling point has increased a lot. Do you see? It's now only like negative maybe 95. Do you see? So this is now, because now all of a sudden there's quite a chance that one molecule attracts another molecule because of induced dipole forces. Slightly induced dipole forces. I see here, it reminded me that other words that can be used as van der Waals forces, London forces, or dispersion forces. Can you understand? London forces just, van der Waals forces, just the names that are given to by the people that discovered it or defined it in theories. But dispersion forces, can you also see how dispersion forces make sense? It's as the electrons are dispersed in the molecule. Okay?
Sorry, so can I ask? I got confused. If the temperature is negative, why is it gas?
So remember, what is its temperature? I'm not saying the temperature is negative. We're saying it boils at that temperature. We're saying temperature is 25 degrees. I want to know what's happening at room temperature. In other words, this substance at room temperature is in what form? If I know it boils at negative 90 degrees, 190 degrees, well, in this case, let's look at ethane now. It boils at negative 90 degrees, but I'm already at 25 degrees. In other words, I'm at this temperature here.
Yes.
Ethane started boiling even when water is freezing. It was boiling. Even lower than that, at negative 90 degrees, it was already boiling. Is it still difficult to understand?
It's negative, like shouldn't that be so?
I don't. Sorry.
Like it's negative.
What is negative?
Temperature.
Temperature is not negative. The boiling point is negative. In other words, if the boiling point, if I am now currently, if I can change the temperature in this room, in here on the desk, I've got some ethane in a container. You can't see it because it's a gas. Okay. If I can reduce the temperature less and less and less to negative 90 degrees, then it will start condensating on the side. Do you understand? If I can reduce the temperature to negative 90, it means if the temperature, let's go back to this diagram. If the temperature is more than the boiling point, if room temperature is more than boiling point, it means I've passed the point where the substance boils. So now it's boiling. The whole time it's boiling. If I bring it into that temperature, it's boiling. And so it is in gas form. Does that make sense? So it will start boiling the moment I'm more than negative 90 degrees. Does that make sense?
Yes.
You should 100% sure.
Yeah, I was lost. I'm okay now.
But are you sure?
Yes.
Okay, awesome. Awesome. But don't worry, and yesterday's class was exactly the same. There's a little bit of misunderstanding about if I talk about boiling point. Boiling point doesn't mean I'm at that temperature. It's the temperature at which I must get for this substance to go from this form to that form. I can be at any temperature. Okay, and then I can decide, well, have I boiled yet? Have I melted at that temperature? That makes sense? Okay. So, let's go back there. Notice now, in this table, if I've got 3 carbons, that would be at about 3 carbons, I'm at about negative 40 degrees. You see? So at 3 carbons, I would be, what would I be at room temperature? Propane at room temperature would be, if I boil at negative 40 degrees at room temperature, which is 25 degrees, it will still be a gas because it started boiling at negative 40 degrees. Okay. Oh, here's an interesting one. So we had methane, ethane, propane, butane. Butane starts boiling at 0 degrees. So when water freezes, methane boils. Butane, sorry. But can you see how the forces in butane is stronger than the forces in propane, ethane, methane? Okay, now you can see that the moment I get to 5 carbons is, was it pentane?
Yes.
That looks for me to about 30 degrees, maybe even more. So at room temperature, what is the alkane, the first alkane to be a liquid at room temperature? Pentane. You get that? Yeah. It should be at room temperature. Pentane should be a liquid at room temperature. Can you understand why? Because now pentanes boils only at 30 degrees, and when I'm at room temperature, I'm not at 30 degrees yet. If I heat it just a little bit, okay, like even if you were to put it in your hand, it will start boiling, okay, because your body is 38 degrees Celsius. So as your body is heating up the substance, if it gets your body temperature, it will start boiling. That would be weird. I'm gonna do that. Do that as a.
Is it 38 really? 38.
37.5, I think. The body's temperature. So if you were to hold it in your hand in a little test tube.
Is it constant at 37.5?
Yeah. But you can ask the life sciences people.
What's keeping it to that level?
Okay, so let's look at the next one. So here at the bottom we have melting points. Now melting points work slightly different. You can see it's not as smooth a curve as this one, but it still represents the intermolecular forces. As you can see, as it gets bigger, the melting point, remember melting point is where I go to a solid if I was a liquid, or I go from a liquid, liquid to a solid, or from a solid to a liquid. Okay, now look, what is the first, how many carbons do I need to be a solid at room temperature? About 19, do you see? So room temperature is about 25, it's about 19. Can I tell you that most of you are familiar with an alkane that actually has 22 carbons? It's called a candle. A candle has 22 carbons, and a candle is solid.
Carbons.
So that candle wax is carbon 22, hydrogen 24. And then another one everyone is familiar with is octane. It's petrol. So petrol is octane.
Oh.
And how many carbons does octane have?
8.
So according to this table, in what form will octane be at room temperature? We know petrol is
Liquid.
Let's see if petrol obeys the rules. Okay, where's 8? It's about here. There it will melt, and there it will solidify. Sorry, boil.
Yeah.
So here it will, below this. So at room temperature there, we can see this. Everything in between here will be liquid. So all these things here will be room temperature will be liquids at room temperature from about 8 carbons to about 13 carbons will be liquids. More than, not 13, 18. More than 18 carbons should be solids. And more than 5 carbons should be liquids, less 5 carbons should be gases. Okay. Is that okay?
And above that is gases,
Yeah,
and then
if
liquid,
you're-
and then gases.
Exactly, yeah.
Sorry.
Is that okay? Can I move on?
Yeah.
Good. So that's very helpful to understand what is meant by induced dipole forces. This is sometimes, very often we call this van der Waals forces, and they're weak forces. But as the molecule gets bigger, they get stronger. Okay, so that a molecule of about 22, 19 would be a solid, because the induced dipole forces is actually strong enough now for those molecules to keep each other together. Okay, so we've looked at when carbon bonds to hydrogens. Now, the next one a carbon can bond to is a halogen. So we have carbons and hydrogens, that very weak forces, unless we have long change that causes that induced dipole forces. carbon and halogen. Who knows what the halogens are?
Bromine and chlorine and fluorine, because they fluoride.
Yeah, it's those. It's all of the ones in column 7. Fluorine, chlorine, bromine, and iodine. And ethylene. I think it's ethylene, but we don't use that one. It's fine. Okay. So one thing you'll notice about these ones are they are all quite high in electron negativity. Except for iodine. Iodine is quite strong, and bromine, quite weak. Bromine is also quite weak. But iodine's size is big. Bromine's size is quite big. Okay? So what happens when we have a carbon now bonded to one of these oaks? Okay, let's put them in red. Okay? If it is something like fluorine or chlorine, then they are really big, and then they're attracting really with a lot of attractive force, which means, now look, for example, if we have carbon and fluorine, 4 minus 2.5 is 1.5. You see, it's almost an ionic bond. That's how strong fluorine is. So if we look at this, obviously we're going to assume that the rest, can I not press every single button on the screen? The rest is all filled up with hydrogens. So there's a hydrogen, hydrogen, hydrogen. The carbon is filled up with hydrogens, the rest. Fluorine is there on that side. Now, because he's pulling so hard, the electrons are definitely congregating on fluorine's side. So this thing is definitely polar, okay, in a sense. Now, the moment that happens, I have, what do we call it if we have poles? Polar, but we call it dipole, because so this is dipole forces. And why is it dipole forces? It is not, this is induced dipole, this is dipole forces. In other words, fluorine is a high electron negative. He is a dipole himself. He starts off being negative, so he is dipole himself. So now he causes a dipole, so he's dipole. They produce dipole forces. The same now goes for if this was bromine. So chlorine, bromine. Bromine starts getting a little bit low because now we're at 2.5 and 2.8. But the size of bromine, remember they increase in size. Bromine's size is now big enough so that we have both this induced dipole forces and we have we have dipole forces, very slight because the difference is slight, but we also have induced dipole because he's a large molecule himself. So the size of the molecule affects induced dipole forces. Does that make sense? So he has two forces, dipole, very slight dipole forces, and very slight induced dipole forces. Okay, so let's go see on the internet if we can find. Okay, so again, look now, when carbon is bonded to just hydrogen. Okay, so here they say we've got carbon and 3 hydrogens. So if we have carbon and 4 hydrogens, this is our boiling point. Now look what a difference it makes if we just change that carbon to a fluorine. You see, it's almost half of that. So this one, the fluorine, now again, fluorine is a very small molecule. So there's not a lot of induced dipole forces that's happening because of its size. Okay? Then chlorine, he has a large electronegativity, which means it's quite polar, but on top of that, he also is also a larger molecule. So chlorine has both induced dipole and dipole-dipole forces because of chlorine's size and the fact that he's attracting electrons. Bromine, you can see, he boils at 3.6 degrees Celsius, and that is mainly because of his size. Okay, he's not attracting with that much electrons, with that much electronegativity. And iodine, again, iodine is a very big molecule compared to the rest of them. Okay, so do you also see, but I just want you to notice actually the difference just between these two, because fluorine is only slightly bigger than a hydrogen. Okay, and yet fluorine almost doubles the boiling point. You see that?
Yes.
Okay, it looks like halving, but it's not really. And the reason for that is because fluorine is really attracting a lot of electrons from the carbon molecule, and so the forces between them is quite strong. Now again, the only thing that this means down here is that now they're just adding a carbon link in the chain. That's what they mean by this. So here we've got a carbon with 3 hydrogens connected to another carbon with 2 hydrogens, and that carbon and 2 hydrogens gets another hydrogen. So look here, this is the table of ethane, ethane, propane. There was that one we saw that boiled at freezing point. That was butane, pentane, hexane. Now again, look on this side. It's just, and I haven't said it now, but the naming for these ones are still the alkane names, but the moment it gets a fluorine, it becomes fluoromethane. So this is fluoromethane, chloromethane, bromomethane, iodomethane. And this one, ethane. So this is ethane, fluoroethane, chloroethane, bromoethane, iodo. So now look again how the boiling point increases. So based on this, what is the first fluoroalkane that is a liquid at room temperature?
The first isn't it butane? Isn't it butane?
Fluorobutane. Fluorobutane. Fluorobutane would be a liquid, while normal butane would be a gas. Okay? What is the first chloroalkane that would be a solid at room temperature?
Chloropentane? Maybe not. I don't know.
Chloro? Actually, we can't tell. These are boiling points. Sorry, I was confusing the question. These are all boiling points. So you don't know when it melts based on this table. Okay, but based on the table, at room temperature would be somewhere between these two, which means at this point it would be a gas, at that point it would be liquid. So this is still liquid, then it's a gas. No? Other way around. This would be a gas. At this point it would be boiling. So this one at room temperature would be a gas, this one at room temperature would be a liquid. You understand? Because he's only going to boil at 46 degrees. Cool. Can I move on?
Yes.
Great. So are you guys happy with? And so the same thing applies when I have an alkane. So when I have a haloalkane, it can be on any one of the carbons. Okay, whichever carbon, and I'll again number so that my alkane would be the first, or the smallest number. So for example, if I have a bromine there, and I have 1, 2, 3, let's say I just had 3, then this would be 2 bromo, 3 propane. Fine? Okay, I'm going to move on. The next one a carbon can connect to is carbon connected to oxygen. Now you're going to see that from now on we're going to focus on oxygen. Carbons bonded to oxygen. Now when we look at organic chemistry, or at least the ones we're going to work with, it's either going to have an oxygen or not. Okay? If it has an oxygen, it can either be an alcohol or a carboxyl. Okay, what's the difference? An alcohol has oxygen single bonded to a carbon. In other words, oxygen has 6 valence electrons.
So sorry, what about ketones?
A ketone is a carboxyl.
Really?
Yeah, I'll show you now. So alcohol or oxygen has 6 valence electrons. If he shares one of those valence electrons with a carbon, he still has 1 left. He could share a valence electron with a carbon and then have a double bond with carbon, or he could get something else on that one, and in the alcohol case, it takes on a hydrogen. Okay. Now, what did we see earlier? When oxygen and hydrogen bond, what do we call that bond? We call, when hydrogen bonds with a high electronegative element, oxygen is second highest. We call it hydrogen bonds. In other words, the forces that exist in alcohol is hydrogen bonds. Hydrogen bonds. Now, oxygen is 3, carbon is 2.5, so there's even a slight negative coming from the carbon towards oxygen, and there's quite a large negative coming from the hydrogen, so the oxygen is quite highly negative charged. Okay, make sense?
Yes.
So there's very strong forces in alcohol. As a matter of fact, ethanol, that means 1 carbon bonded, is already, sorry, that's 2 bond, is already a liquid at room temperature. Okay, well remember, when we look at ethane, was a gas, the first one that was a liquid was with 5 carbons, was it 5 carbons? I don't remember how. First with 4 carbons. Okay, so this one, I think, is actually the methanol. Yeah, even methanol is a liquid. In other words, just with 1 carbon, it's already a liquid. Does that make sense? So in other words, the size, and it's a small molecule, because oxygen is small, hydrogen is small, okay, carbon is small. So it's a small molecule, and yet there's these strong forces. Why? Because oxygen is pulling so hard on hydrogen and carbon, and then electrons are congregating towards it. Make sense? And so that's called hydrogen bonds. Okay, now a carboxyl is when we have carbon bonded with oxygen. In other words, where both of those bonds went to carbon. So now notice the difference between the forces that will exist here. Here we had hydrogen forces, which are strong forces. Usually hydrogen bond forces are liquids. Okay, because it's really quite strong forces keeping the molecules together. In carboxyl is when I have an oxygen double bonded to a carbon. Now remember, carbon had 4 that he could bond with, so he still has 2 left. Okay, but here what we find is a high electronegativity with carbon, the same as with halogens. So the forces that will exist in carboxyls are dipole-dipole forces. So high electronegative element with carbon will be dipole-dipole. Low electronegative will be induced dipole. Is that okay?
Yes.
And then it's all about the size of the molecule. Now we get different carboxyls. Okay, 4 different ones. The first one is when this carbon just bonds to a hydrogen. Okay? And on this side, it can just be any combination of, we call it an alkyl group. Alkyl is the same as alkane, but it's just an alkane is a finished structure. And alkyl means that, so for example, this, if there's hydrogens all around here, this will be an alkyl because he can still connect to something. Okay, if he connects to a hydrogen, it will be an alkane. Okay? So in other words, what I'm saying here is like a normal alkane structure. It's just carbon, a hydrocarbon, carbon and hydrogen. Okay, so in that case, this is called aldehyde. Aldehyde. I remember aldehyde by the H. It's a carboxyl just bonded with a hydrogen and then a substituent or an alkyl group. Make sense? So what forces do we encounter in aldehydes?
Isn't it?
Dipole-dipole. Only hydrogen bond forces if hydrogen bonds to oxygen or chlorine. Hydrogen bonding to electronegative. This is carbon bonding to oxygen. In this case, with alcohol, it was different because yes, oxygen was bonded to carbon, but that's not what causes the hydrogen. This bond here is actually dipole-dipole. This bond here is hydrogen bond. You get it? But together they form a very strong bond because both of them contribute to oxygen's negative ability. Okay? Or negative property. Aldehydes will end on the suffix al. So if I name them, you guys know this, I'm not going to focus on that. That's simple enough. But for example, if I have one carbon in this chain of alkyls, in other words, I'm only connected to another hydrogen, this would be methanol. Between methanol and methanol, which one do you think has the strongest forces?
Methanol.
Methanol. And then we can prove it. I'm not going to go there, but we can actually go and look at the boiling points. Which one, if methanol has the strongest forces, which one will have a higher boiling point?
Methanol.
Methanol, because it takes more energy to break the bonds. Make sense? Not the bonds, to overcome the intermolecular forces. Okay. The next one that we can have is if this is an alkyl group and that is an alkyl group. In other words, this carbon here, or no, the carboxyl for an aldehyde is on the end. That's the difference. It's on the end. For a ketone, it is somewhere in the middle. Does that make sense? So ketone, and it ends on an O-N-E. And ketones would be okay, you can't get a methone because the methone will have H here and H there, one carbon. It's no methone, it will be methanol. Does that make sense? Because both of these, so the smallest ketone I can get is if I have a carbon here and a carbon there. You get that? So the smallest ketone I can get will be propone.
question because aldehydes and ketones are a subsection of carboxyl. Will they mark it right if we say it's a carboxyl acid instead of saying it's a ketone? I mean, it's a carboxyl instead of saying it's a ketone.
This is not, guys. These are not. This is called a carboxyl functional group. Okay, it doesn't mean if it has that it is a carboxyl. There's now something else called a carboxylic acid. That is something else now. So in other words, a carboxyl is the carbon double bonded to oxygen.
Okay.
Do you understand? So carbon double bonded to oxygen, there's 4 types of them. And these will all be called, how do you pronounce it? Homologous series, something like that. Homologous series, is that how you pronounce it? And homologous. Say it out loud.
Homologous series.
That wasn't out loud. Anyway, there are things that have only one thing different. Okay, so things are in that series if they have only one thing different. So all these things, these are from that series because they only have one thing different. This one has extra carbons than that one on that chain. The next one, carboxylic acid. So carboxylic acid, okay, acid ends on oic acid, and a carboxylic acid will have, so this one had the substituent H, this one had the substituent, we use an R to represent an alkyl chain. This one ends on an OH. In other words, what type of forces will be the strongest in our carboxylic acids? What type of forces do exist in carboxylic acid? Yes, and hydrogen bonded to oxygen.
So there's hydrogen and what?
There's hydrogen bond forces. Hydrogen bond forces. And dipole-dipole forces. Dipole-dipole forces because of the oxygen and carbon. Hydrogen bond forces because here instead of an alkyl group I have a hydroxy group. You get it? So here would be the question. Which one will have the strongest forces? Methanol or methanoic acid?
Methanoic acid.
Why?
Because hydrogen bonds have strong forces.
Methanol also have hydrogen.
Wow.
Isn't it because of there are two? It's like, okay, let's put it in the same. We have the alcohol, the methanol team there, and the methanoic acid.
Yeah.
The methanoic acid team consists of 2 strong men, and the methanoic only consists of one strong man.
Perfect.
So
That's a great way of understanding it. There's 2 types of forces acting in methanoic acid. Both the dipole-dipole from the carbon and oxygen, as well as the hydrogen bond forces. So again, if you go and look, and I did with yesterday's class, I'm just taking a different approach today. I actually went and looked at methanoic acid, their boiling points, and you can clearly see there's a difference, actually quite a big difference between their boiling point, and methanoic acid is much higher. Okay. Now the last one we get is esters. And an ester has this carbon double bonded to oxygen, and remember that these are all the carboxyl group as from the series. But this one, so on the one side he's got a carbon chain, okay, on the other side he has an oxygen that's single bonded to the carbon, and this oxygen also has a substituent, another chain. Okay, now in naming this one, we will name this the alkyl. So this one will actually be a branch, and this carbon chain on that side, okay, this one will actually be the one I count, how many there are. And so I will count, I will start with my alkyl group, I'll call it a branch, so it will either be methyl, well, it will be whatever the alkyl name is, alkyl. If it has one carbon, it's methyl. 2 carbons, ethyl. 3 carbons, butyl. So no propyl. 4 carbons, butyl. You with me? And then we will name the ester side of it. It's not really the ester side, the carboxylic side of it. The carboxylic side of it will be a normal alkane, methane, but it will end on O8. So methanoate, ethanoate. So just as an example, if I have 2 carbons, the one carbon is double bonded to the oxygen, single bonded to the oxygen, and this one is bonded to one carbon like that. Okay. Then I have, this will be my carboxyl. Okay. So that is going to form the main name. In this case, it is ethanoate. I've got my E there. And on the branch side, I only have one carbon, so I've got a branch called methyl. And I don't need to number for the branches because the branch will always be on the oxygen anyway. Okay, makes sense? You get it? Now, what forces exist in esters? Your turn to think.
Esters. We have dipole.
Well done. Dipole. We have dipole forces between the carbon and the oxygen, and the carbon and the oxygen. So for example, if I just had, I don't know if this is a real compound. Okay, this one will have, this will be methyl, methanoate. Okay, which one will have a higher boiling point between methyl methanoate and and so let's also choose another carbon with or let's go for carbon, 2 carbons, so let's go for ethanoic acid. Okay, and also ethanol. Let's go for that. Which ones do you think will have the highest boiling point? Which one will be in the middle? Which one will be lowest?
I'm thinking ethanoic acid would be number 1, ethanol number 2, and methyl methanoate number 3.
Okay,
Yes.
so let's go for Pendile. You vote 1, 2, 3. Okay. Yeah.
Ethanoic acid number 1.
Yeah.
But number 2 is methanol. Yeah.
And then this one number 3. So Olivia Bacani.
Wow. Always Pendile.
Sorry?
I'll follow the same thing that
Pendile.
Yeah.
Pendile.
Say
Like that. Okay. So justify why you say
Because
ethanol is less than methyl ethanoate.
I think because methanol methanoate has the weak intermolecular. What's this process between?
Why?
Because can boil it at a low temperature, very low.
No, so in other words, something doesn't have weak intermolecular forces because it boils at a low point. It boils at a low point because it has weak intermolecular forces. Do you understand? It is not, it's, for example, I'm not sick. I don't have a cold because I'm sick. I'm sick because I have a cold. Do you understand? You're putting the wrong cause and effect. So you are saying it's got weak forces because it boils at a low temperature. No, low temperature, yes, it is the evidence that it has weak forces, but it's not the reason why its forces are weak. The reason why its forces are weak are determined by the polarity of the molecules, on whether the molecule, so if I ask why is something weak, forces, you don't tell me because it boils at a low temperature. That's the consequence of having weak. I want to know why does it have weak forces. Do you understand? So yes.
Isn't it because it has more branches?
Because it has
More branches.
That's possible, but it doesn't really have branches. This is still a straight chain. Okay, we haven't looked at branches yet. I'll show you branches in just a moment, the effect. But this, even though we call that a branch, it's not branching off, it's branching on. You understand? So it's not like I'm putting it on the side here. I'm putting it in on the side from here. You understand?
Yes.
So it's not that much branched, but that would have been a better answer than your first one. Well, you're going to stop getting the right answer because or the right reasoning because you have the wrong answer. Olivia, why would you justify yours as such?
Because methyl has an extra branch.
Will that help?
Thought so.
You thought so. Okay, so I haven't spoken about branches yet, so I won't ask you guys a question about branches if I haven't spoken about it. I'll agree with Olivia because methyl ethanoate has two dipole-dipole forces. It has this dipole-dipole and that dipole-dipole. While ethanol only has that dipole-dipole force. So it's like, previously we were talking about the two strong men. It wasn't really two strong men. It was a man and a strong man pulling against only a strong man. Here I have two men and the other one only has one man. Do you understand? So in other words, ethanol only has that negative molecule, oxygen pulling electrons towards there. Ethanol are pulling oxygens towards electrons towards there and electrons towards there. So he has a negative on that side, a positive on this side, and a positive on that side. Understand? Okay, can you understand why? And it's called theoretical science. This is not tested. This is theorizing based on your theory. You're making conjectures. Doesn't mean you go and actually do the boiling, do the investigation, see if it actually is like that, and if you have made the right conjecture. Okay, so I can't say it's really like that, but that is how you would do science. Is you would create theories based on or predictions based on your theories, and then you go test your predictions. Okay, great. Let us move on from here. Okay, it's a good point to get to branching. Why does branching affect the intermolecular forces? Okay, now first of all, a lot of times I hear teachers and I read in textbooks, they talk about the surface area,
Yes.
and they talk about that the surface area is directly, so they say that intermolecular forces are directly equivalent to surface area. Okay, but let me give you intermolecular the formula. So force, some of you might be at charges already in the course. If you are, you'll know that the force that exists between two charges is equal to K, the charge on one molecule, times the charge on the other molecule divided by the distance squared. Okay, so intermolecular force is directly equivalent to the product of the charges and indirectly equivalent to the distance between the charges. But what are the charges? In our case, the charges are molecules with a positive and a negative charge, and another molecule with a positive and negative charge. The more positive, in other words, the more I have an electron rich, let's say electron rich is in red, electron poor is in blue. Okay, so if I'm only slightly electron rich, I'm more pink, and I'm more a light blue. Okay, so this molecule is, he's got a bigger difference in his charges than that one. Okay, so the forces that will exist between two of these will be stronger because the charges on each of those are stronger. Okay, but now when it comes to surface area, why does surface area have an effect? Surface area has an effect because we're talking about a larger molecule. Now when the molecule gets larger, what is increasing? What type of force starts existing?
When what gets larger?
If the molecule gets larger, in other words, the surface area is increasing when the molecule itself gets larger.
It's IMF.
Sorry?
IMF.
No, IMF is what you call intermolecular forces. What type of forces starts to exist when the surface area increases? Okay, so in other words, induced dipole forces don't exist until the molecule gets bigger and bigger and bigger. So all molecules experience induced, so all of those bonds, so even in a dipole-dipole bond, dipole-dipole forces, when the molecule gets bigger, all of a sudden we also have induced dipole. It's like adding a bunch of small men pulling. You understand? So that will help any guy. Okay, whether you're a strong man against another strong man, if we can get another man on my side, even a weak man, the more weak men I have, the stronger we will become. Does that make sense? So surface area has got to do with that. That when my chain length increases in size, I am increasing the charge that comes from induced dipoles. Does that make sense? All of the forces comes from charges. The bigger my molecule is, the more likely I am to have induced dipole. Okay, does that make sense? Now, the other thing that affects it is what? Distance between the charges. Now, in our case, what we talk, if I mean charge, I'm talking about a molecule. So, what is the distance between the molecules that will affect the forces that exist between the molecules? For example, you guys use underarm spray, I'm sure. Okay. When you spray it under your arms, is it a liquid or a gas? It's a gas.
Yes.
Okay. That gets sprayed against your arm and condensates, gets pulled up in your arms. But in the bottle, it's a... That's odd. What?
But then when you, yeah,
It's a liquid. Why, if you spray it, is it a gas? Like, what's going on there?
Isn't it? When it's
chemistry. It is, but it's not magic. What is the difference between the in the can and outside of the can?
In the can, they have little space, and then outside the can, they have a bigger space, so they have more energy to move, so less collisions happen, and therefore they are less.
Okay, so it's not really collisions, but you are 100% correct. Remember, what I want is, if something is a gas, it means that the force keeping them together is less than the kinetic energy. Now, how can I increase this force? Either by increasing the charges or by decreasing the distance. So what do you have in a can? It's compressed. This can is compressed together. So the molecules have less space to move around, which means they're closer together, which means the force between the molecules are stronger because they're closer together. Make sense? And as a result, they're a gas. But now what happens, they're not a gas, they're liquid. Now what happens, they get released into the atmosphere. There's no more pressure keeping them close together, so their kinetic energy is enough to escape.
When you spray, you don't think it's
No, you don't, but now you will.
Yeah, I know.
Another thing is, when you spray, so remember what's happening now. Once it is released, it has more kinetic energy. Okay? Now I'm going to make a fool of myself if I try and explain this. But what I wanted to say is you'll feel that can is always cold. Okay? That is because when you touch it, the molecules inside is getting energy from you. Do you understand? So if something is cold, it is because it's pulling energy out of your hand. If something is hot, it's because it's giving you energy. So something feels hot, not when it's hot, but when it's hotter than your hand, when it has more energy than your hand has. Do you understand? Okay. And not just that,